All right, let's dive in. Today we're tackling a really powerful technique for A-level maths, combining partial fractions with binomial expansions. Now this is a classic exam topic, and trust me, by the end of this, we're going to break it all down into a simple, repeatable process. So let's get started.
So, you've probably seen a fraction like this before, right? With a bunch of different factors in the denominator, and you've thought, how on earth am I supposed to expand that? It's a totally fair question, and I promise by the end of this explainer, you're going to have a rock-solid method to solve it, no problem.
So here's our plan. We'll start with the why these two topics even go together. Then we'll look at the two key tools you need. After that, we'll walk step by step through a master example. Then we'll try it out on a few different types of problems before putting it all together on a real exam question. Let's do this.
So why do we need to smash two different concepts together? Well, it's because some algebraic fractions are just too messy to expand directly. We need one tool to break the problem down into smaller, manageable bits, and then another tool to do the actual expansion. Think of it as a really elegant 1-2 punch.
And here they are, our two main tools for today. Our whole strategy is going to revolve around getting really good at using partial fractions and the binomial expansion. Let's take a quick look at what each one actually does.
Okay, so partial fractions are basically our deconstruction tool. They let us take one really ugly fraction and split it into several much simpler ones that we can actually work with. Then, once we've got those simple pieces, we bring in the big gun, the binomial expansion. That's what lets us turn each of those simple pieces into a long polynomial series.
You can think of this slide as our cheat sheet for the whole session. Over on the left, you've got the three main ways to set up your partial fractions. And it all depends on what the factors in your denominator look like. And on the right, that's the binomial expansion formula we're going to be using over and over. These are the two patterns we really need to get down today.
All right, enough theory. Let's get our hands dirty and see how this actually works. We're going to go through a complete example from the textbook, worked example 7.12, really slowly and carefully. This is where you'll see it all click into place. So here's our problem. Notice we've got two different, nice, linear factors in the denominator. That means our first job is to split this thing into two separate fractions, and then our second job is to expand it. Okay, now the key to finding a and b is this really cool trick with substitutions. To find b, we want that a term to just disappear. How do we do that? We make the bit next to it, the 1 plus x, equal to 0. So we sub in x equals -1 into that whole equation in step 2. The left side becomes 10 -1 plus 1, which is -9. The a term is gone, and we're left with b times 1 minus 2 -1, which is 3b. So -9 equals 3b, which means b has to be -3. We do the same thing to find a. Make the 1 minus 2x term 0 by subbing in x equals 1/2. It's a brilliant shortcut. And just like that, we've done it. We've broken down our big, complicated fraction into two much friendlier pieces. Now we can get to work and use the binomial expansion on each one of them separately.
Let's expand that first term. We'll rewrite it as 4 times 1 minus 2x to the power of -1. Now, using our formula, the expansion is 1 plus n times our x term, so that's 1 plus -1 times -2x, which simplifies to 1 plus 2x. The next term is n minus 1 over 2 factorial times our x term squared. If you keep following that pattern and then remember to multiply everything by that 4 out front, you get this full expansion right up to x cubed. Now for the second term, we do the exact same thing. It becomes -3 times 1 plus x to the power of -1. We just apply that binomial formula all over again. But this time, n is -1 and our x term is just x. That gives us the series you see here once you distribute that -3 through everything.
We are so close. All we have to do now is combine our two expansions. This table makes it really clear. We just line up the coefficients for the constants, the x terms, the x squared terms, and so on, and then we just add them together. That gives us our final coefficients. Simple as that. Okay, one last absolutely crucial detail, validity. These infinite series only actually work for certain values of x. For our first expansion, it's valid when the modulus of minus 2x is less than 1. That works out to x being between -1/2 and 1/2. The second one is valid when the modulus of x is less than 1. So for our combined expansion to work, both have to be true. That means we have to take the stricter, more narrow range, which is -1/2, less than x, less than 1/2.
Awesome. Now that we've totally nailed the core method, let's have a look at a couple of common curveballs you'll see in exercise 7e.
These problems just introduce a slightly different challenge right at the beginning, in the partial fraction setup.
So our first new challenge is, what do you do when you have a repeated factor in the denominator? Something that's squared.
Here's the problem. See that 1 minus x squared? That's the key. That's the difference. It means we need a special kind of setup for our partial fractions.
And the crucial point here is that setup. A repeated factor like 1 minus x squared needs two terms in the decomposition, one for 1 minus x and another one for 1 minus x squared. Once you've got that form right, you find your constants. The substitution trick will help you find b and c pretty quickly, but to find a, you might need to try something else, like comparing the coefficients of x squared. After that, the expansion process is exactly the same for all three terms, and it leads you to this final result.
Okay, next up. What if your denominator has a quadratic in it that you just can't factorize any further? This adds another little wrinkle to our partial fraction setup.
Have a look at this one. That 2x squared plus 1 term, there's no way to break that down into linear factors. And that means we need a different approach for that part of the decomposition. And here's the rule you've just got to remember. A non-factorizable quadratic on the bottom needs a linear term, bx plus c, on the top. Once you have that correct setup, you solve for your three constants, a, b, and c. This usually involves a mix of substituting to find a and then maybe comparing coefficients to find b and c. Then you just expand each part like we did before to get that final series.
All right, we've seen the main method, and we've seen two of the trickiest variations. Now let's put everything we've learned together and apply it to a full exam-style question. This is where we see if we can do it under pressure. This exam question really has everything. Step 1, we spot the quadratic and set up our partial fractions with a bx plus c on top. Step 2, we find our constants. Step 3, we rewrite them so they're ready for expansion. Now, Step 4 has a classic exam trap. For the term x minus 4 to the negative 1, we need it in the form 1 plus something to use our formula. So we have to first rewrite it as negative 4 plus x to the negative 1 and then factor out that negative 4. After you've carefully expanded both of those tricky parts and collected all your like terms, you arrive at that final answer.
Phew! Okay, we have covered a lot of ground. So after all those examples, what is the single core repeatable strategy that you should walk away with?
It really just boils down to these 5 steps. First, and this is the most important step, look at that denominator and pick the right setup. Is it linear, repeated, or quadratic? Second, hunt down your constants, a, b, and c. Third, rewrite your simple fractions so they're in the right form for expansion. Fourth, carefully apply the binomial theorem to each part. And finally, fifth, combine everything by just adding up the like terms. If you can follow these 5 steps, you can solve any of these problems.
When you step back and think about it, this whole process is a really powerful tool for approximation. We're taking a messy, complicated fraction and turning it into a simple polynomial that's pretty accurate, at least for small values of x. So that leaves us with a final thought. Where else, maybe in science or in engineering, could this power to approximate complex functions be an absolute game changer? Thanks for tuning in.